Hello, everyone. So far, we've mostly been talking about the different hazardous classifications for chemical compounds. However, turns out there's a lot of chemicals out there, and it can be kind of important to have a good system so you can quickly identify what hazards you might be working with. So today, we're going to be focusing in on hazard identification. So before we do that, I want to go ahead and start with today's wonderful little safety moment by talking about an incident that happened at Mizzou just down the road about 10 years ago in the summer of 2010. So this particular picture was taken right after a biochem lab exploded. So yes, uh, disastrous chemical reactions aren't just for chemists, they're also for biologists. In this case, what they were doing is they were looking at studying anaerobic bacteria. So they were working in a isolated hood. That may be that fallen over thing you see there in the center. Now, when studying anaerobic bacteria, you often will feed in hydrogen into your cells. So they were feeding in hydrogen to their bacteria. And well, turns out there was an ignition source. Turns out nobody's quite sure what it was. But thankfully, only 4 people were injured. No one was killed. And where everyone should really end up being thankful is you may notice in the center of this picture, there's the 4 cylinders sitting that used to be next to the hood untouched. It's well agreed upon it would have been quite disastrous if anything happened to those cylinders. But there was still well over $1 million worth of damage. And again, this was mostly because people weren't thinking about the chemical dangers that are present even when working with biological samples. And I wish I could say this was an isolated incident, but a little bit more catastrophic version happened in Hawaii at about the same time. Again, largely because people weren't thinking that just because they weren't in a chemistry lab that they didn't need to be in mind of what chemical hazards might be present. So one of the most important things you can one of the most important things when you're working in a chemical lab is to make sure you are able to easily recognize any hazards that might be present in the lab. And this means that one of the most important tools you have on hand is signage. And it unfortunately occurs that there are several different types of signage you may end up encountering when dealing with chemical hazards. So the quickest and most familiar form that you may have seen before is the NFPA, or National Fire Protection Association's diamond. So this is the classic chemical diamond, which is a way to quickly convey the most important dangers when interacting with a chemical. So you may have seen one of these sitting on the door to a lab or sitting on a truck driving down the highway, where we divide the hazards of a chemical into 3 major categories: health, fire danger, and chemical reactivity. This one is often rephrased as chemical stability, which again focuses a little bit more on how stable the compound is, and again, less on what we traditionally think of as reactivity, due to chemical reactivity having a little bit more to do with what other systems it may be present around. However, this white diamond at the bottom is essentially the catch-all for special warnings. So some of these should look familiar because we've been talking about them for a while. You may see a shortened name for essentially acidic, corrosive, or alkaline sort of behavior. There's also our good old biohazard, poisons, radioactive, just being too dang cold, or the big 3 you should watch out for: water reactives, oxidizers, or just an asphyxiant. But again, as we talked about a lot last time, watch out for water reactives and oxidizers, and please never let the 2 touch. So with this major idea in hand, let's go ahead and dive in a little bit more into our health diamond. So for example, the one I provided for you right here is the health diamond for ethanol. Yes, it turns out that ethanol is more dangerous than you might think. So let's go ahead and talk about what these individual numbers end up meaning. So for example, when I look at health, I'm evaluating health risks on a 0 to 4 scale. 0 being not hazardous at all, and 4 being extremely dangerous. These have a rough analog to our good old friend, the LD50, where if something is considered non-hazardous, this tends to be my LD50 is somewhere greater than about 2,000 milligrams per kilogram. So think about something like acetaminophen. Maybe a little toxic, but generally you'd have to consume a fair bit. 1 is going to be slightly hazardous, meaning it's probably going to cause you some damage, maybe acute, maybe chronic. But again, this is going to tend to have LD50s going somewhere in between 500 to 2,000 milligrams per kilogram. And it's worth noting that this actually can contain some fairly dangerous species, such as hydrogen peroxide actually lands in this category with an LD50 of around 1,500. That doesn't mean that it won't do you a lot of damage. It probably just won't kill you. Similarly, several insecticides, including rotenone, also end up landing in this category. So again, just because there's a 1 doesn't mean it isn't dangerous. And don't forget, ethanol can definitely kill in sufficient quantities. 2, categorized as hazardous, typically has an LD50, anywhere from 50 to 500. So this can actually be some quite toxic compounds, but includes some things that while dangerous, we often don't think of so, such as nicotine or caffeine. Or again, watch out when you're dealing with the pure species. Once you get to 3, then you really have to start watching out because we have LD50s essentially less than 50 milligrams per kilogram. So this includes things like cyanide sitting at about a 10. Turns out vitamin D is also more dangerous than you think. With it also has an LD50 of about 10 milligrams per kilogram. And then by the time you get to 4, these are very much extremely poisonous. So extremely dangerous. So these are a lot of your strong poisons and include things like strychnine. So this is, again, LD50s less than 5, with strychnine having about a value of 2. So again, hopefully that gives you an idea of what we're talking about with non-hazardous to extremely dangerous, where there may be a lot more complications to those simple numbers than you think. Similarly, we have our classic fire rating. So 0 means it will not burn. Pretty much even if I take an ignition source to it. 1, essentially, I have to heat it up before I hit a flash point. So again, this is going to typically belong to species with flash points above room temperature. And again, 2 is where you're going to run into species that may actually start having respectable auto ignition temperatures, as well as probably a flash point below room temperature. And again, 3 guarantees that you have a flash point below room temp, which it turns out ethanol does. So at room temperature, an ignition source will ignite. And then 4 means watch out. It's going to ignite at the drop of a hat. Then for stability, 0 means that it's stable. I don't really have to worry about it getting up and doing something unkind. 1 means that, okay, it may end up reacting with itself upon mild heating. And then by the time you get to 2, this is where you really have to start watching out because it may undergo a violent self-chemical reaction. So these are things that may start detonating. 3 means that, again, any strong shock or heat may detonate. So do not heat the sample, do not hit it with a hammer, be very cautious. 4, hopefully never work with anything like that. And again, it's worth noting, you can look up most of your NFPA diamonds for relevant chemical species at any number of sites. I provided several available resources for you here. Now let's go ahead and try and take these kind of arbitrary numbers and work through some examples. So again, I've got ethanol. Biggest danger here is the of ethanol is that it is actually fairly flammable. Otherwise, Molotov cocktails wouldn't be a thing. But also, don't drink too much of it; it will kill you. Acetone, pretty much approximately as flammable and a little bit more toxic. So please don't drink any acetone, I beg you. But again, the big danger of both of these are going to be the flammability. By the time you get to acetylene, well, this one ends up being a little bit more interesting, as acetylene is quite flammable. Again, not quite as toxic as acetone, but still fairly toxic, but a little more dangerous because it exists in the gas phase. So it's going to be easier to ingest sufficient toxic quantities. But one of the big things that stands out with acetylene is it turns out that it actually is self-reactive because it can undergo an exothermic polymerization reaction. So watch out that you don't heat it up too much. You can run into some issues, and this is one of the reasons why acetylene tanks are known for causing problems. Then we talked a lot about this last time, nitric acid. And despite how many warnings I gave you about this, you'd expect to see a worse NFPA diamond. But it turns out it's mostly occurs in aqueous conditions, so very much not flammable. It doesn't react with itself at all. Okay, it's quite toxic, so please watch out for that. But the real danger actually comes from here, the oxidative reactivity. Because while it might not react with itself, it loves reacting with other things. So again, watch out for this white square, because that can be a fairly, that can hide a lot of things that might not be present in the other squares. We also have things like chloroform, which isn't really flammable because chlorinated organics are often used as fire suppressants. It's fairly stable with itself and actually fairly unreactive. Unfortunately, it's also quite deadly. And again, one of the things that makes it a little bit more dangerous than the number might make you assume is it's also in the gas phase, which, as we saw with acetylene, might make it a little bit more likely to run into problems because you're more likely to reach any sort of threshold value. Then we have our good old friend diethyl ether. So again, like chloroform, this one used to be used as an anesthetic, which was mostly, it's mostly not used now because it turns out it can have some long-range health effects as well as some acute ones. But one of the big reasons people like getting away from diethyl ether is that it turns out that it evaporates quite readily and that vapor is quite ignitable. Again, the extra oxygen group on it, again, as well as higher volatility, makes it a little bit worse than ethanol with that respect. Though again, it's quite stable on its own. Then we have, say, sodium hydroxide, where it has some stability issues if you, depending on hydration state, not flammable at all, but again, it can turn you into soap. And then you get to really nasty compounds like fluorine, which is going to be quite toxic because it's going to share a lot of toxicity with chlorine gas. But we also have to watch out with the fact that it's highly reactive, including the fact that it's a water reactive. It can, well, react with it, self-react and detonate. And again, not too surprisingly, with those quantities, health hazards. So we see quite a gambit all across a series of species that you'll probably work with at some point in time. So again, before you end up working with any species, I highly encourage you to kind of get familiar with what hazards they possess. And note that there may be some things that will leap to the forefront or are easier to ignore, such as any sort of warning that comes along in this bottom element. Now, because a lot of information can hide in those special reactivity conditions, there's been a move to move away from the NFPA system and move to the GHS system, which is the globally harmonized system. So the idea behind the GHS system is I'm going to mark a hazardous room or chemical with essentially a pictorial symbol, and then below it I'll say exactly what kind of dangers that might be described with this symbol. For example, when we see this exclamation mark, it tends to mean that we have an irritant, but it can also include things like dermal sensitizer, things that show only acute toxicity that are harmful but not deadly, narcotics, or things that are just respiratory tract and irritation. So again, these are things that hurt but won't kill you. This stands in contrast to our good old sign for flammables, but is worth noting that it can also include things like self-reactives, pyrophorics, self-heating, flammable gases, and organic peroxides. So just because you see the symbol, don't assume that you only have to worry about flammable organic solvents. There may be a lot worse in there. So again, it gives you a general idea of the danger, but there's always accompanying words that give you the details. Then for more chronic toxicities, we see the health warning, which tends to include things that have more longer term effects, such as carcinogens, respiratory sensitizers. So these are ones that make you more vulnerable to long-term issues. Reproductive toxins, toxins that target specific organs, which may include kidney or liver function, which you won't see immediately, but can have some real long-term effects, mutagens, and things that can do lung damage. So these ones are ones that are going to have a lot more chronic, long-term toxicity. You might not see them right away, or they may make you vulnerable to other things, such as in today's current culture, if you're exposed to a respiratory toxin, you have to be very aware to stay away from COVID because you're going to be much more vulnerable. Then we have our good old symbol for oxidizers. And oxidizers are so special that, yes, they get their own symbol because, again, this is a warning to keep them away from things like organic solvents. Then we have our good old explosives. So this is, again, if I have a particularly violent type of self-reactive, then instead of just heating or slowly igniting, can cause rapid gas buildup, well, then those special classes of organics and peroxides get their own kind of special warning. But again, all dangers aren't strictly chemical. For example, we have our good old gases under pressure. Because it turns out it isn't just David Bowie who's under pressure. It's also Freddie Mercury. Then again, corrosives. So these can be species that are damaging to either people or tissue or to surfaces. And as we've seen before, maybe both. And then our good old friend, acute toxicity. These are things that will kill you. But again, it's not just you have to worry about. There may be things that you need to be very aware to not flush down the drain or to release into the air because they may have wider environmental toxins. And again, it is worth noting that there may be several keywords that go along with these symbols that may indicate the severity of the hazard. So for example, we'll watch out for fatal, which is going to be the most severe, followed by toxic, then harmful, then may be harmful. So again, watch out because our keywords often our symbols often come with keywords, and our keywords may come with modifiers. Now let's go ahead and just like we did for our hazard diamonds, let's go ahead and repeat some of familiar chemicals with our GHS system. So for example, if I have methanol, it tends to be flammable, highly. It does actually a little more flammable than methanol due to its higher vapor pressure. But it can also have chronic toxicity as it tends to target specific organs such as eyes and liver and kidney, but also in sufficient amounts, it is quite fatal. So again, this is why people often talked about the issues of methanol poisoning or denatured liquor. So don't buy cheap moonshine. It may contain methanol. It may send you blind or kill you. There's our warning system. But we also have things like chloroform, which tends to be much more of an irritant and a carcinogen. With specific organ preference for skin and eyes. Then we have our good old friend acetone, which is flammable. It's also an irritant, but it turns out it likes to also target uh, nervous system, spleen, kidneys, and liver. So if you like your organs, I highly encourage you to not ingest the acetone and try not breathe it in too much. Then we have sodium hydroxide, with the big dangers here tending to be from corrosivity, which can do damages to surfaces and tissue. So again, we're separating the health damages from more long-lasting terms to essentially saying it can destroy what it has direct contact into. And please don't make the water too basic. We like our fishies. And similar, we see similar behaviors for hydrochloric acid with a little reduced environmental toxicity and a little bit increased irritant damage. And then we also, for the biologists out there, have things like ethidium bromide, which tends to be used in DNA staining. So if you're going to be running a lot of gels in biochemistry, you're probably going to use ethidium bromide. And it turns out that it can be actually quite toxic if it's inhaled, so please don't, but it's also a more long-term carcinogen. So, all right, I've spent all of this time giving you a huge list of hazards for common chemicals. Now here's the question. Where did I find all this information? Because it turns out you might want to find it too. And there's a number of sources out there, as I showed previously with the NFPA diamonds. But it's also worth noting we have our good friend, the safety data sheets. And it's worth noting that these tend to replace the older material safety data sheets. So we currently call them EMET or SDSs, but you may see someone in older materials referencing MSDSs, as this was the older name. And one of the wonderful things about SDSs is that if you sell a chemical, you're required to be able to provide an SDS sheet that presents all of the information that might be relevant to somebody who's working with them. So if you're working in a lab, there should be an SDS sheet, either available in hard copy or increasingly in some sort of digital database. If you cannot find them, please ask the instructor, because you should know the danger of every single chemical you're working with. However, it turns out that they are fairly widely available online and pretty easy to locate in our digital age. So a good place to start with is a lot of chemical production companies. I highly suggest a good place to start is Fisher, but a lot of individual universities and other companies tend to contain an SDS sheet. So what's available on an SDS sheet? So it's composed of 16 parts that are mostly self-explanatory. The chemical ID information, which may include multiple different chemical names, as many chemicals will be recognized by several different names, as well as things like CAS numbers. Identification of any potential hazards, the composition and purity of the species. This tends to especially go with the SDS sheets provided by companies, as they need to say exactly what sample was provided, because it turns out that different hazards may go with different compositions of a species. And in addition, you don't want to just know the hazards, you also need to know what to do in case you're exposed to it. So response measures are often going to be included on the SDSs, including both first aid and firefighting. And, well, is there anything else I should do to prevent it from getting out in the wild? This one can be incredibly important sometimes, like with mercury. And similarly, what do I need to do to prevent things from going wrong? And this may include things, especially with certain volatile species, what sort of temperatures you should maintain the sample at. Because it turns out, as we've seen, making sure that you keep a sample well below its autoignition or flammability temp can be very important. And again, based on these dangers, what sort of personal protection should you end up using? And then more practically, as a chemist, and less from a safety aspect, knowing the physical and chemical properties. So things like melting point, as well as other potential things such as molecular weight that are just generally good information to have. And again, related to that, stability and reactivity. So again, what conditions do I need to keep the sample stable? And what should I, under no conditions, react it with? And again, similarly, what sort of toxicological damage may end up needing to be, may the chemical have, which may end up relating to see item number 4. And again, similarly to release, what sort of ecological damage it may do. And to avoid that sort of issues, how should I dispose of the chemical? And is there any special information I need for transport or regulatory information, such as, is this a controlled substance? But because it turns out that even this might not be enough information, we do have an other category. So as you may have noticed, the SDS is one of the most complete sources of information you can go to if you need help knowing what sort of dangers you may have using a new chemical. So let's go ahead and take a look at an example SDS sheet. So here we have the SDS sheet for acetone, where we start with including numbers like, hey, what's my product name? What are other synonyms, CAS numbers? How can I find it under the company website? Again, provided by Fisher. Where do I go for help? Specific hazards that may end up belonging to acetone. As I said previously, flammable, loves damaging eyes, loves to target the nervous system, and kidney, liver, spleen, and blood. Again, this one more from repeated exposures. So again, there's a lot of information present here. And again, a lot more information on their hazards. Then we have all of our various GHS symbols, how to prevent too much exposure, what to do if you think you may have been exposed, which essentially go to a doctor. If you inhale it, so again, fresh air is most important, especially because a lot of the time it's under inhalation. And then good old fashioned, if exposed to skin or eyes, rinse it off. In case of fire, CO2 or dry chemicals, probably try and not work with water. It tends to spread the fire. And again, first aid measures, firefighting measures, including information like auto ignition temperatures and flash point. And again, here's our upper and lower explosion limits. So again, here's where it's going to be flammable. So we have a lot of information: accidental, handling, exposure controls. So again, we have our TLV values, our OSHA values, as well as other sort of metrics, both in terms of long-term and short-term exposure limits. Engineering measures, so again, eye wash stations and good ventilations being the biggest thing. Physical properties ranging anywhere from pH to odor, which can be incredibly important if you need help IDing a species. Though some of these specific information, the importance of some of the specific information may depend on the chemical you're using. We also have things like, hey, I might need to know its vapor density or specific gravity to help identify the species, as well as things like solubility in water, viscosity, and molecular weight. So we have a lot of useful information. Reactivity, turns out it isn't, and it's mostly stable. Avoid oxidizing agents, reducing agents, strong bases, peroxide, so pretty much anything strong. And again, so there's a lot of information here. So I highly encourage you, the next time you're working with a chemical, whether you think it's hazardous or not, please go ahead and look it up, because it's worth noting I have all of this information and a lot of dangers for a chemical you're probably using on a weekly basis in your organic lab. So again, I highly encourage you, make use of the safety data sheet. It's going to be a lifesaver. Hopefully not literally, but it might be. So next time, we're going to be talking a little bit more about hazard information and proper sample labeling. Until then, take care.